Welcome to The Explainer. Today we're going to tackle a computer science concept with a name that's, well, famously misleading: dynamic programming. But what if I told you it has way less to do with coding and a lot more to do with just being smart about not doing the same work twice?
So let's just say it. The name dynamic programming sounds kind of scary, right? If it does, you're definitely not alone. But the story behind the name is actually pretty surprising, and it reveals that it has almost nothing to do with what we think of as programming today.
And this quote really hits the nail on the head. See, the term was invented by a researcher named Richard Bellman way back in the 1950s. And back then, the word programming just meant planning or scheduling, like TV programming or planning a military operation. It had absolutely nothing to do with writing code on a computer.
So get this, Bellman himself later admitted the name was basically a marketing ploy. He was doing some pretty advanced mathematical research, and he needed to get funding from government officials. And those officials wanted to fund projects that sounded practical and important. So dynamic programming just sounded way more impressive than what it actually was, a multi-stage decision process.
Okay, so if it's not some special kind of coding, what problem is it actually solving? Well, it all boils down to one super simple idea: avoiding repetitive work. It's really just an optimization strategy you use for problems that keep asking you to solve the exact same smaller problem over and over and over again. To really see this in action, let's look at a famous example, the Fibonacci sequence. You probably remember this one. Each number is just the sum of the two numbers that came right before it. It's a classic example of a recursive problem.
Now, if you write a simple recursive function to find, say, the fifth Fibonacci number, you hit a snag, and you hit it fast. To get F5, you need to find F4 and F3. Okay, simple enough. But to get F4, you also need to find F3. Do you see it? We're about to calculate F3 from scratch again. This kind of wasteful repetition just explodes as the numbers get bigger.
This mess leads to something called exponential time complexity, or O of 2 to the n. And in plain English, that's horrible. It basically means the amount of work you have to do roughly doubles for every single number you add to the sequence. It becomes impossibly slow really, really quickly.
So what's the brilliant fix for this mess? It's almost laughably simple. Just don't do the same work twice. That's it. That's the entire core of dynamic programming. Remember the answers you've already found so you don't have to figure them out again.
And there are two main ways to pull this off. First is the top-down approach, using something called memoization. Think of this as the recursive method, but with a cheat sheet, or a memo. Before you calculate anything, you just check. Hey, have I solved this before? If the answer is yes, you just grab it from your cache. The second way is the bottom-up approach, which uses tabulation. Here, you solve the tiniest possible problems first, put them in a table, and then build your way up, step by step, until you get to the final answer.
Okay, so that's the theory. But how do you actually spot a problem out in the wild where you can use this technique?
Well, technically, a problem is a perfect candidate for DP if it has two key things going on. First, optimal substructure. That's a fancy way of saying that the solution to the big problem is built from the solutions of its smaller pieces, just like how f of 5 is built from f of 4 and f of 3. And second, overlapping subproblems. This is that wasteful part we just saw, where you're forced to solve the exact same smaller problems again and again. But honestly, in the real world, it's often way easier to just learn to recognize the common patterns. If a problem is asking you to find the minimum cost or the maximum path to a target, or if it's asking you to count the number of ways to do something, there's a really, really good chance that dynamic programming is the way to go.
Let's make this feel a little less abstract and apply this logic to another classic problem.
So the problem is this. You're climbing a staircase. You can take one step at a time, or you can take two steps at a time. The question is, how many different ways can you get to the top? Well, this fits our distinct ways pattern perfectly. And if you really think about it, the number of ways to get to any step n is just the number of ways you could have gotten to the step right below it, plus the number of ways you could have gotten to the step two below it. Wait a second, it's the Fibonacci sequence again, just in disguise.
So instead of using that messy recursive approach, we can just build a simple table from the bottom up. We start with the easy stuff, the base cases. There's only one way to get to step 1. There are two ways to get to step 2, 2 single steps or 1 double step. From there, the answer for step 3 is just the sum of the last two, so 1 plus 2 is 3. For step 4, it's 2 plus 3, which is 5. We just iterate our way to the top. No repeated work at all, just clean, fast, and efficient.
So after all that, what are the crucial points you should really take away about dynamic programming? First, and most importantly, just remember it's all about being efficient by stopping repetition, avoiding redoing work you've already done. It works for problems that can be broken down into smaller puzzle pieces that get reused. You can solve it from the top down with that memoization trick or build from the bottom up with the table. But really, the secret superpower is just learning to recognize the patterns when you see them.
It's really a perfect example of a powerful idea that was just hiding behind a complicated name. We started with this intimidating term that was really just a marketing gimmick for military funding, and we ended up with a beautifully simple tool for solving really hard problems. It's a tool that's used everywhere, from calculating flight paths to sequencing DNA. And it all just comes down to asking one simple, kind of lazy question before you start. Hey, have I solved this before?